Hello and welcome. Today we're going to look at another problem with binary trees. It's Leetcode 222, count complete tree nodes. Given the root of a complete binary tree, return the number of the nodes in the tree. According to Wikipedia, every level, except possibly the last, is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. It can have between 1 and 2 to the age nodes inclusive at last level age. Design an algorithm that runs in less than O(n) time complexity. And here we have an example, 1, 2, 3, 4, 5, 6. So this is a complete binary tree. It doesn't have to have all leaf nodes. So you can see here there's one missing, but they're populated from the left side. That's one of the properties of the complete binary tree. And if it would have all of the leaf nodes here, so if we would have another, if node 3 would have a right child, for example node 7, then we would say the tree is a complete binary tree. More on that later. So in this case the output is 6, we have 6 nodes, and if we have no nodes the output is 0, if we have one node the output is 1, and here we have some constraints. So the tree is guaranteed to be complete for this problem. Okay, so the catch here is that it says that we have to design an algorithm that runs in less than O(n) time complexity, but actually we can start with the O(n) algorithm. So it's a simple depth first search. We just say, okay, int count left is count nodes of root left, int count right is count nodes of root right, and then return 1 plus count left plus count right. And of course we still have to check if our root node is empty. That's our base case. We return 0, and that should be it for the O(n) solution. Yeah, and actually you can see that it's accepted, even though they are saying in the problem statement it's supposed to be better than O(n). This is an O(n) solution and it's accepted. So now let's think a bit, how can we improve upon the time complexity for this problem. So we might have a better time complexity. I have this line here, so this is what we are going to achieve. We will achieve a logarithmic time complexity. So how are we going to do this? So let's go to the drawing, and here we have our tree from the example, and we can see that our tree has the 6 nodes but also the 7th node. So we are considering a perfect binary tree, not just a complete binary tree, and that's because perfect binary trees have an interesting property. If you see, node 1 has a level 1 in the tree has 2 to the 0 nodes, or 1 nodes. Level 2 has 2 to the 1 or 2 nodes, and level 3 has 2 to the 2 nodes, or level 0, 1 and 2 if you prefer. And the property is that the sum of all of these nodes would yield 2 to the power 3 minus 1, or in general 2 to the power age minus 1, but in this case we would have 2 to the power 3 minus 1 nodes. And if you count the nodes, you can see there are 7 nodes. So we got the correct result. So we're going to use this property of the perfect binary tree in order to compute our result, our count. So what we can do is, at each step we can check if our tree is a complete binary, is a perfect binary tree, by going on the edges, the left-right edges, all the way down and here. So we're going all the way on the left side and all the way on the right side. And for a perfect or complete binary tree, the height size is going to be, the computation of the height is going to be done in logarithmic time. Because like we said before, we have 2 to the h minus 1 approximately. So if we take h out of that equation, we get the logarithmic time, and we have to go on the left side and we have to go on the right side. So in total we have to compute two heights, the left height and the right height. So in total we will have 2 times log of n. And then we check if left height is equal to right height, we return 2 to the h minus 1 left height, because it's a complete binary tree. Okay, so if it's a perfect binary tree, we return 2 to the left height minus 1. And if not, we continue recursively, and in this case we need to go forward to the next node. So if we add node 7 here, it's not going to be the case, because we already have these two subtrees. We already have them as perfect, as equal, so it will detect a perfect tree. So if we consider this subtree and this subtree, right, if 7 is in there, it's going to be a perfect binary tree, and we're going to just return 2 to the height minus 1, and that's it. But if not, we have to go to node 2, and then we compute again if this node in its search space in this subtree is perfect, which it will be, because we have 4 and 5, and then we compute also for node 3 if it's perfect. And here it will not be the case, because we're missing node 7, and so on and so forth. So that's how this algorithm works. So we check again the leftmost and rightmost edges of each tree, and then we split our search space in 2 and continue splitting it. So this is kind of a binary search, so the recursive calls will also be logarithmic inside. So we have again another binary search, we have another log n from here. So in total, at each step we have to do 2 log n times log n. So that yields 2 times log n squared, so that's log squared n. Sorry, not n squared, but log squared n. And that's going to be our final time complexity. And our space complexity is going to be logarithmic, because our tree is complete. And again, as I said before, the recursive calls would split our search space in 2 as we go down on each tree branch. So we'll have it as a logarithmic space complexity. If the tree could be skewed, which is not the case for a complete tree, it would be a log of n for the recursive stack, but in this case it's just logarithmic in time. Okay, so let's go and code the solution. Okay, so I'll just remove the previous code here, and we can start coding it up. Actually, I could have left the first line. Okay, so now we're going to compute the left height. And then we're going to compute the right height. And then we're going to check if left height equals right height. So here, check if we have a perfect binary tree. We return 2 to the left height minus 1. Maybe it's clear like this, or we could also do pal of 2 left height minus 1, but using bit shifting should be faster. Okay, and then we want to return 1 plus count nodes of root left, count nodes of root right, in case we have a regular node that we don't have a perfect binary tree. So now let's write the two helper functions. So we start with height view while node height node is node left. Turn height and get right height. Get right height. Node height plus plus. Node is node right. So return height. Okay, so it returns the left height, returns the right height if they equal. The tree is perfect, and we just return our result, which is 2 to the power left height minus 1. And otherwise we keep going recursively through the search space and compute the count like that. And let's see, this works. Accepted and accepted. And like I said here, space complexity is going to be O of log n. Okay, that's it for today. I hope this helps you understand the problem. If you did, please like and subscribe, and stay tuned for more C++ problems. Thank you and bye.